Engineers spent nearly 100 years of relentless research just to keep trains running on electric power. This is the history of the pantograph. It may look like a simple device, but solving its problems was anything but easy. The earliest pantograph designs were relatively simple. They consisted of a copper conductor and a spring mechanism. The copper conductor used spring tension to press against the overhead wire. This allowed electricity to flow to the motor, but a lack of stability and excessive friction made the equipment prone to damage. To improve stability, engineers redesigned the copper conductor with a backward tilt. They also reworked the spring and support structure of the pantograph. This significantly improved overall stability. But a new problem soon emerged. The spring tension was difficult to control. It could easily damage the overhead cable, so engineers added a pull rope at the rear to counterbalance the spring force. That solved the problem. To make the wire connection more precise, engineers added a slotted tube at the contact point. But over time, another issue appeared due to the train's continuous operation. The metal slot inevitably wore down from constant use. It required frequent replacement, so engineers replaced the contact head with a long metal strip. The cable was also redesigned in a zigzag pattern. This constantly shifted the contact point along the strip, increasing the contact area. It greatly reduced wear on the contact head. To further reduce wear on the overhead cable, engineers added carbon strips to the contact surface. This allowed the pantograph to run smoothly, even at high speeds. The side angles were also extended and improved. This new design was called the bow collector. It helped trains smoothly switch between overhead cables during track transitions. Without it, the wire could get caught underneath the collector head. But as train speeds kept increasing, this design began showing new weaknesses. The main issues were air resistance and vibration, caused by turbulence forming behind the collector. To fix this, in 1903, engineers redesigned the pantograph. They switched to a double-arm symmetrical structure, which successfully eliminated the vibration problem. Drivers could also manually adjust the pantograph height by observing the cable level. But the double-arm pantograph was bulky and heavy. It was neither energy efficient nor flexible in operation. To address this, engineers used new technology. They developed the single-arm pantograph, which features a 4-bar linkage at its base, with the contact head mounted at the end of an extended yellow arm that can be adjusted flexibly in height. However, the angle of the contact head changed along with its height. This made contact with the overhead wire less effective, but engineers solved it with a clever design. Introducing a balance bar. The balance bar connects to the lower arm. It extends up to the collector head and also forms a 4-bar linkage. The balance bar applies a counter torque that cancels out the rotation of the contact head. As a result, the collector head stays perfectly level at any height. The lower arm rotates using a pneumatic piston, allowing the pantograph to be raised or lowered as needed. The entire design is simple and efficient. It has remained in use to this day. In short, the pantograph is a true marvel of engineering. It provides reliable power to modern, high-speed trains.